According to the National Electrical Code, specifically Section 310.15b3, if current carrying conductors are paralleled in more than 3 raceways, or in more than one layer within a raceway, unless the conductors are transposed at regular intervals of not more than 24 inches, which is equivalent to 600 mm, the allowable ampacity of each conductor shall be reduced as shown in Note 4 of Table 310.15b2. Now, Note 4 of Table 310.15b2 directly addresses paralleled conductors numbering between 3 and 9, inclusive. In situations involving more than 9 paralleled conductors, a clarification is needed regarding derating requirements. To address this specific scenario, an inquiry was made to the NEC Codemaking Panel 1, seeking clarification on derating requirements for paralleled conductors exceeding 9 in number. The response received from Mr. Kent Strebel, Chairman of Codemaking Panel 1, provides valuable insight. The panel's intention is that all conductors, regardless of quantity, paralleled in more than 3 raceways, or in more than one layer within a raceway, unless the conductors are transposed at regular intervals of not more than 24 inches, shall have their ampacity reduced in accordance with Note 4 to Table 310.15b2. The revised text for 310.15b3 to accomplish this will be if the current carrying conductors are paralleled in more than 3 raceways, or in more than one layer within a raceway, unless the conductors are transposed at regular intervals of not more than 24 inches, which is equivalent to 600 mm, the allowable ampacity of each conductor shall be reduced as shown in Note 4 of Table 310.15b2. It's important to note that this change is not intended to change the current requirements, but rather to clarify them. Therefore, the answer to the initial question is yes. Derating of current carrying conductors is necessary when paralleled in more than 3 raceways, or in more than one layer within a raceway, even if the total number of conductors exceeds 9, unless proper transposition is implemented. Understanding the National Electrical Code requirements for derating parallel conductors is crucial for safe and compliant electrical installations. Section 310.15b3 and Note 4 of Table 310.15b2 provide guidance on ampacity adjustments when conductors are paralleled in multiple raceways or layers. Let's delve deeper into the key aspects of these requirements. Firstly, when conductors are paralleled, the current is divided among them. However, the heat generated by each conductor contributes to the overall temperature within the raceway. To prevent overheating and potential insulation damage, derating factors are applied to reduce the allowable ampacity of each conductor. Secondly, the number of current carrying conductors within a raceway influences the derating factor. As the number of conductors increases, the heat generated rises, necessitating a greater reduction in ampacity. Note 4 of Table 310.15b2 specifies the derating percentages based on the number of conductors. Thirdly, the arrangement of conductors within the raceway also plays a role. When conductors are arranged in multiple layers, heat dissipation becomes less efficient, leading to higher temperatures. Similarly, when conductors are installed in more than 3 raceways, the heat generated in each raceway could affect the others. Fourthly, transposition is a technique used to mitigate the effects of unequal impedance among paralleled conductors. By regularly interchanging the positions of the conductors, impedance imbalances are minimized, resulting in more even current sharing. When conductors are properly transposed at intervals of not more than 24 inches, derating may not be required, even when the conductors are installed in multiple raceways or layers. Fifthly, it is essential to consult the latest edition of the National Electrical Code for the most up-to-date requirements and interpretations. Codemaking Panel 1 provides valuable insights and clarifications on complex issues related to electrical installations. To summarize, when paralleling conductors in more than 3 raceways or layers, derating is generally required unless the conductors are properly transposed. The derating factor depends on the number of current carrying conductors and the specific conditions of the installation. Adhering to these requirements ensures safe and reliable operation of electrical systems. Let's consider a practical example to illustrate the application of derating factors. Suppose you need to install 11 sets of 4 500 kc conductors from a transformer to a 480 volt switchgear, resulting in a total of 44 conductors. These conductors are to be installed in separate conduits, with each conduit containing 4 conductors. According to the NEC, since the conductors are paralleled in more than 3 raceways, derating is required. To determine the appropriate derating factor, consult Note 4 of Table 310.15b2. This table provides derating percentages based on the number of current carrying conductors in a raceway. In this case, each raceway contains 4 current carrying conductors. Referring to the table, you'll find the corresponding derating percentage. Apply this derating factor to the allowable ampacity of the 500 kcmil conductors to determine the adjusted ampacity. Ensure that the adjusted ampacity is sufficient to carry the intended load current. If the adjusted ampacity is insufficient, you may need to increase the size of the conductors or reduce the number of conductors in each raceway. Additionally, consider the impact of ambient temperature on conductor ampacity. If the ambient temperature exceeds the specified temperature rating of the conductors, further derating may be required. It's crucial to perform accurate calculations and consult the NEC to ensure compliance with all applicable requirements. Ignoring derating requirements can lead to overheating, insulation damage, and potentially hazardous conditions. By understanding the principles of derating and following the guidelines outlined in the National Electrical Code, you can ensure the safe and reliable operation of electrical systems. In conclusion, derating of parallel conductors is a critical aspect of electrical installations. By understanding the NEC requirements and applying the appropriate derating factors, you can prevent overheating, ensure conductor longevity, and maintain the integrity of the electrical system. Remember to always consult the latest edition of the National Electrical Code and seek clarification from qualified professionals when needed. Proper planning and execution are essential for safe and compliant electrical installations. Transposition is another measure that is crucial in electrical installations with parallel conductors. When multiple conductors are used in parallel to carry a large current, ensuring equal current sharing among them is vital for efficient and safe operation. Unequal current sharing can lead to overloading of some conductors, causing overheating and potential failure. Transposition involves periodically interchanging the positions of the conductors along their length. This technique helps to balance the impedance of each conductor, minimizing differences in inductance and resistance. By minimizing impedance imbalances, current is distributed more evenly among the conductors, reducing the risk of overloading. The National Electrical Code specifies requirements for transposition in certain situations. When conductors are paralleled in multiple raceways or layers, transposition is often required to avoid derating. The NEC mandates that conductors be transposed at regular intervals of not more than 24 inches, which is equivalent to 600 millimeters. The specific method of transposition can vary depending on the installation. One common method involves rotating the conductors within the raceway or layer. Another method involves physically interchanging the positions of the conductors at regular intervals. The goal is to ensure that each conductor occupies each position for an equal amount of time. Proper transposition requires careful planning and execution. The intervals between transpositions must be consistent and accurately measured. The conductors must be securely fastened to prevent movement or displacement. The connections at each transposition point must be properly made to ensure good electrical contact. When done correctly, transposition can significantly improve current sharing among parallel conductors. It reduces the risk of overloading, extends conductor lifespan, and enhances the overall reliability of the electrical system. However, it is important to note that transposition may not be necessary in all situations. When conductors are closely spaced and symmetrically arranged, impedance imbalances may be minimal, and transposition may not provide significant benefits. In such cases, other measures such as using conductors of equal length and size may be sufficient to ensure adequate current sharing. Therefore, it is essential to carefully evaluate the specific conditions of each installation and consult with qualified professionals to determine the appropriate course of action. In addition to transposition, other factors can also affect current sharing among parallel conductors. Conductor size, length, and material all play a role. Variations in these factors can lead to impedance imbalances and unequal current distribution. To minimize these effects, it is recommended to use conductors of the same size, length, and material. The connections between conductors and equipment are also critical. Poorly made connections can introduce resistance and impedance affecting current sharing. Therefore, it is essential to use proper connection techniques and ensure that all connections are clean, tight, and corrosion-free. Regular inspection and maintenance of connections are also important to identify and address any potential issues. In summary, transposition is a valuable technique for improving current sharing among parallel conductors. It helps to balance impedance, reduce overloading, and enhance the reliability of electrical systems. However, it is not a one-size-fits-all solution and should be implemented in conjunction with other best practices. Careful planning, proper execution, and regular maintenance are essential for achieving optimal performance. The National Electrical Code serves as a comprehensive set of guidelines for electrical installations. It is developed and maintained by the National Fire Protection Association, a non-profit organization dedicated to reducing death, injury, and property loss due to fire, electrical, and related hazards. The NEC is updated every 3 years to reflect advancements in technology, changes in industry practices, and lessons learned from incidents and accidents. Compliance with the NEC is mandatory in many jurisdictions. Electrical inspectors use the NEC as the basis for evaluating electrical installations and ensuring that they meet minimum safety standards. The NEC covers a wide range of topics related to electrical installations, including wiring methods, overcurrent protection, grounding, equipment installation, and special occupancies. It provides detailed requirements for conductor sizing, raceway fill, equipment spacing, and other critical aspects of electrical design and installation. The NEC is organized into chapters, articles, and sections. Each chapter covers a specific area of electrical installations. Articles provide more detailed requirements for specific topics within a chapter. Sections contain specific rules and regulations. The NEC also includes tables, figures, and annexes that provide additional information and guidance. These resources can be helpful for understanding and applying the code requirements. Navigating the NEC can be challenging, especially for those who are not familiar with its structure and terminology. However, there are several resources available to assist users. The NEC Handbook provides explanations and examples to help users understand the code requirements. Training courses and seminars are offered by various organizations to provide in-depth instruction on the NEC. Online forums and discussion groups provide a platform for users to ask questions and share information. It is important to stay up to date with the latest edition of the NEC. Changes and revisions are made with each edition to address emerging issues and improve safety. Failure to comply with the latest edition of the NEC can result in fines, penalties, and potentially hazardous conditions. The NEC is not intended to be a design manual. It provides minimum safety requirements, but it does not provide guidance on how to design an efficient or cost-effective electrical system. Engineers and designers must use their professional judgment and experience to develop designs that meet the specific needs of each project. The NEC is also not intended to be a substitute for qualified electrical contractors and installers. Electrical work should only be performed by individuals who are properly trained and licensed. Qualified professionals have the knowledge and skills to perform electrical work safely and in accordance with the NEC requirements. The NEC is a valuable resource for ensuring the safety and reliability of electrical installations. By understanding and complying with its requirements, you can help to prevent electrical hazards and protect people and property. In addition to the NEC, there may be other applicable codes and standards. Local building codes may have additional requirements that must be followed. Industry standards may provide additional guidance on specific topics. It is important to research and comply with all applicable codes and standards.